All right. Well, so hopefully that was not, anything startling or anything you hadn't seen before and so on. And I will get that graded in the next few days along with Lab 4, which I hope to have finished sometime today. And usually after I give an exam, I'll go ahead and grade it and kind of see what the sort of overall issues might have been, and then talk about those in the next class. But if there's anything that anybody wants to ask about the exam right now, something that's gonna keep you awake all weekend or whatever, we can certainly talk about that. But then I'll plan on going through the whole exam on Monday. But anything anybody wants to ask at this point, go for it.
Nothing to ask, but I think it's funny that there was a question on there with the decimal and the decimal number, the 2.625.
Mm-hmm.
And I literally added a note in there thinking, oh, that probably won't be in the exam, but it should be in there anyways.
Ah, okay.
On the exam, I was like, oh my gosh.
Okay. Yeah, that one is not worth too many points because that's something we talked about but haven't really done a lot. But obviously the first two parts of that question were the heavier weight parts because binary and two's complement. All right, cool. We'll leave it at that for now, and then like I say, I'll get this graded over the next few days, and then Monday we'll go through the whole exam, and I'll talk about whatever I saw in general, whatever issues seem to come up for multiple people, and so on and so forth. What about other questions? So you're working on Lab 5, which is the 555 timer and the counter. So that should be wrapping up soon, and you're at least looking hopefully at homework 5, the state machine design. We just started state machine analysis on Monday. We're going to spend most of the second half of the class today going over more examples of analyzing state machines, but you might have some questions on that. So anything from there that people want to talk about? Mm-hmm.
So in experiment 1, it asks to find the clock cycles, I believe, or the...
So calculate and draw the clock signal?
Yeah, the output.
Yeah.
So I believe you use an oscillator or a oscilloscope for that?
So calculating is done using these equations. So when you have a waveform that's changing over time, typically you see, this is called the high part of it, right, where the logic level is high. This is the low part. So typically you'll see something like, T sub H to indicate the amount of time during which it's high, and T sub L to indicate the time where it's low. And for this particular circuit, we've got these formulas that tell us how long the signal should be high and low based on the resistor values and the capacitor. So you basically plug in these values, and remember, mega is 10 to the 6th, micro is 10 to the minus 6th, so lots of things cancel. And you'll find a number of seconds for high and low, and so based on that, you can draw a sketch, try to make these, roughly proportional to what they should be, because they're not the same numbers. And then, label instead of TH, put down, this is high for 17 seconds and it's low for 20 seconds, or whatever the formula tells you it should be. So that would be the calculating and drawing the clock signal, and then compare the clock signal waveform observed on the output pin. So you could do that with an oscilloscope, but this is a pretty slow signal. It's going to be on the order of seconds for where it changes. So you might be able to get the oscilloscope in Tinkercad to actually show you that, or you may want to just time it, right? Just kind of eyeball how long it's long and try to get a approximate measure like that. Oscilloscope is your best bet, but a real oscilloscope would have a hard time going down that low. Tinkercad may be able to do it though. But mostly I want to see, this sketch, your calculations for what those time periods should be and what the expected waveform is. And then, if you want to say, yeah, it kind of looked like that, or it was hard to time using the oscilloscope, but I used a timer app on my phone and it looked like it was, about this much time. That's plenty.
And so, when you plug into a oscilloscope, it works, but when you use output with an LED, it doesn't, because you have VCC going through a resistor to output. So I was wondering, you're saying like just time it. How would you be able to see it?
You should still be able to drive an LED from this output. If it's not working, then try just taking out the 1K ohm resistor. And just take the output, run it through a series 1K resistor, run it through an LED, connect the other end to ground.
Okay, yeah, I'll try that.
Okay.
Thanks.
Yeah. And the other purpose of that, if you do this on a physical 555 and you look in an oscilloscope, you might be expecting a waveform that looks like this. But if you look at it closely enough, you would find that it actually looks like this. Right, and there's going to be all these imperfections. There's going to be maybe a little dip before it starts to rise. There's going to be what we call ripple, where it actually overshoots the 5-volt level by just a little bit, and then it drops down below and goes above and sort of settles down to 5 volts. But this may not actually be 5 volts at all. This could be, 4.72 volts. And it's not going to go up with this nice vertical rise. It's going to slowly increase. And so with a laboratory version of this experiment, it's a much more interesting comparison, what you actually observe versus what your theory says it should be doing. And we're kind of approximating that in Tinkercad, but Tinkercad is a little bit, too perfect sometimes, which is a good thing. Someone said Fourier series in chat just now, and that's a great little Pandora's box that I will try not to open too much, but when I teach 120, we actually talk about this a little bit when we do the engineering math section, but really, really briefly, it's very hard to build a circuit that will change instantaneously from, say, 0 volts to 5 volts. In fact, I would say under normal circumstances, it's probably impossible. You cannot instantaneously change a voltage. It has to continuously change from 0 to 5 volts. And if your circuitry is very good, you can make this pretty close to vertical. If your circuitry is very slow, it might do something like that. But the theory is, an inverter, if you change the input from 1 to 0, the output goes to 0, 0, 0. Boom, the output's suddenly 5 volts. But this is more of the reality. So there's this notion of something called a Fourier series, and a Fourier series basically says, any waveform that you can imagine that repeats over time can be written as just a bunch of sines and cosines added together. So, a sine wave is just a very regular, position of a point on a wheel over time, for example. And a cosine wave is the same thing, but it starts, a little bit later. And by just taking, different frequencies of this, so squeeze them together or spread them out, and make them taller or shorter, by taking different combinations of those and adding them together, you can create any periodic waveform, including this. And so the more of these you add together, the better you can approximate this. But the other side of that is the better your circuitry comes to actually creating this effect, the more complex the waveform is, the more components it has, the more different sine waves of different frequencies are involved. So if you listen to a square wave through a speaker, it's got this really buzzy kind of annoying sound, right? You can hear all these what we call harmonics, right? Multiples of this basic frequency combining together. If you listen to a perfect sine wave through a speaker, it's a very smooth tone. It's very soothing. It's like the tone they use on film strips when it's time to advance the film strip, if you ever had that in school. It's a very mellow tone, and it could put you to sleep. And all of this is topical in daily life because guess what? When you have digital amplifiers, when you have a digital sound system, when you have digitally enhanced audio, you're doing this, right? You're switching your signals very quickly, and you're introducing all of these harmonics. And so when you play a CD through a very fancy digital sound system, you're not hearing the original sound that was recorded on that CD. You're hearing the artifacts of the Fourier series. You're hearing all of these upper level harmonics, all these extra tones that weren't in the original signal. So how do you get the original signal? Well, if you have electronics that respond more like this, slower circuitry, you can get a more faithful reproduction. Well, how do you find, an amplifier whose circuits are slow? Well, this is where like the old vacuum tube based systems come in. And this is why audiophiles love tube based amplifiers. This is why the good bands use tube based amplifiers, right? Because it gives you a more faithful reproduction. And of course, a record, a vinyl record, right, is a recording of the motion of a needle whose displacement is based on the amplitude of the sound being put into a receiving microphone. And this is an analog recording of that information. A CD is a digital recording of that information, and it does not record the same information, and it introduces these other harmonics. So this is why people will pay, $200 for a vinyl recording of something that you can download, for 99 cents from the web. So that's a whole Pandora's box. So audiophiles will say analog is better than digital. That's certainly, fighting words for some people. Because digital, you can make a perfect copy of the original digital recording, and it doesn't degrade over time. And, of course, you can make backups and so on and so forth. And so there's advantages of that, right? The analog recordings wear out each time that you play a phonograph. The needle is moving in these grooves. Well, it's changing those grooves a little bit. So there's upsides to both digital and analog, but in terms of accurately reproducing the original sound that was used to make a recording, analog is probably a more faithful reproduction. So if you're electrical engineering, you'll take courses like Engineering 204, 252, 253. You'll dig into all of this in great detail, and learn how to do a Fourier analysis and so on and so forth. If you're computer science, right, we don't go over this in other courses, but in computer science, inevitably you're going to at some point deal with digitizing information, doing analog to digital conversion, and back the other way. We'll do a bit of that in Engineering 270 also, and these are just some kind of things to keep in mind as you encounter those. All right, cool. So other questions, comments on labs, homework, audio systems? All right. So let's look at more state machine analysis. So we went through an example last time where we started with this system, this originally had D flip-flops, and we came up with the equations. We converted those into a state transition table and figured out, you know, based on your present state and your input, what is your output and what's your next state. And then from that we came up with a state diagram that showed us how we move from state to state. And then at the end of class we went ahead and said, hey, if these were toggle flip-flops, right, then these equations would have been for the T inputs, and we would have gotten a different state transition table. So, but that was kind of a rushed example. That was just sort of showing where we're going with this. So let's do another state machine analysis, and let's use toggle flip-flops, and then we'll do one with JK. And I want to talk about timing while we're doing this also. So I'm gonna just make this up, and we'll go ahead with two flip-flops. So I'll do T0 and T1. We've got clock inputs. A lot of times when you see these diagrams, the clock inputs aren't even shown as being connected to anything. We understand the clocks are connected together. So most of our flip-flops give us a pair of outputs, a true output and a complemented output. So there's Q1, Q1 bar, Q0, Q0 bar. And I don't know, let's just make something up. Let's take Q0 bar and AND it with X0 and put that into the toggle input. And let's take Q1 and let's feed that into the T0 input. So we're going to keep our equations pretty simple. And let's also take Q0 and X1 and let's OR those to get a Z0 output. And let's take Q1 bar and call that Z1. So this machine looks a little different from kind of a system diagram perspective. It's got two inputs, X0, X1, and it's got a pair of outputs, Z0, Z1. All right, so we talked about Mealy versus Moore machines and Mealy versus Moore outputs, and I don't know if anyone remembers those, but Z0, anybody want to venture a guess whether this is a Mealy or a Moore output, and why? Right, so this output is dependent, well, let's see, said dependent on X0. So Z0 depends on the state of this flip-flop, and it also depends on this input X1. Z1, on the other hand, depends only on the state of this flip-flop. And so this is the distinction we want to make between those two situations. Does the output depend on both the state and one or more inputs, or is it a function only of the state? And then the names for these, and these are, you know, effectively random names. For a Moore machine, this is, you know, depends only on the state. A Mealy output depends on the state and an input, at least one input. All right, well, the Z0 depends on the state. The state is Q0, Q0 bar, Q1, Q1 bar. Z0 depends on the state and an input, so Z0 is Mealy. Z1 depends only on Q1 bar, that's the state, so this is Moore. And that's not going to affect anything until we draw our final system state diagram. And then how we show these outputs will depend on whether they're mealy or more. But all the work we're going to do up to that point is pretty much independent of what type of outputs we have. All right, so how many states do we have? Or how many flip-flops do we have? Yeah, we have 2 flip-flops, so we have 2 squared, which is 4 possible states. So make a state table. So let's start over here. I'll put it over here. So our state is the combination of Q1 and Q0. And we've got 4 possibilities. And I'm going to use a naming convention that is usually what I'm going to use. I'm just going to call this, S for state with a subscript of 00, S01, S10, S11. And this is convenient because, if I know that Q1 is a 1 and Q0 is a 0, I know that represents state 10, right? Just the value of 1 and Q1 and Q0. So that will, sort of automatically code some of my information for me. All right, so now we make the present state, next state table. So we start with present state. And we also have a pair of inputs. We have x0 and x1. Alright, so our inputs are going to be x1, x0, and our state is given by q1, q0. A big sheet of paper is better, but I think we can make this fit. Alright, cool. Alright, so we've got our present state, we've got 4 possible combinations, we've got 2 inputs, 4 combinations of those. We're going to have 16 rows in our state table. Alright, and so now we can fill in our outputs. So let's figure out what Z1 and Z0 look like. Well, let's write some equations. So the equations come from, I think I can write them on here. The equations come just from looking at your circuit diagrams. So I'm writing equations for my outputs and for my flip-flop inputs. So outputs are a little easier here. Z0 is an OR output, and it's the output of Q0 and X1. Z1 is super duper easy to write, it's just Q1 bar. And then let's write our flip-flop inputs. Well, T0 is not bad. T0 is coming from Q1. And T1 is coming from an AND gate. And what are the 2 things being ANDed? Q0 bar and X0. And at this point, right, we're analyzing the circuit. We're just kind of looking at it, and we're trying to write down equations to see what drives the inputs of the flip-flops and what drives the outputs. And this can be tricky. So if you look in the textbook, at some of their state machine questions. Getting there. Right, you've got circuit diagrams like this. You need to be able to sort of like trace the wires, and we can have lots of wires connected together, but in general only one output should be driving a bunch of inputs. So you know, D1 is an input, there should only be one output feeding it. Well, it's the output of this AND gate. D2 is an input, there should only be one output feeding it, and it's the output of this OR gate. But some of these other machines, you may have to do some chasing around and figure out where a signal is coming from. That one's not bad. Well, I don't have a good example of that, but when you have a picture like this, right? If you're trying to figure out what the value of an input is, there may be different wires connected to that, right? One of those wires should be an output, and that output is the thing that's actually putting a signal value, a 0 or a 1, onto that line. So you have to trace that. All right, so here's our equations, right? These are the outputs, these are the flip-flop inputs. So we can fill in our output column now. Z1 is just the complement of Q1, so it's the complement of this column. So Z1 looks like this. And then Z0 is an OR, Q0 ORed with X1. So Q0 ORed with X1, it's these two columns in the middle here. And if any of those bits are a 1, then Z0 should be 1. And so it looks like these top two rows are a 0, but down here we've got 1s on X1. And here we've got 1s on Q0. And here we've got a pair of 0s. And then we'll have 1s on X1, and then we'll have 1s on Q0, so it'll be the same pattern down here. So there's our outputs, and then let's write the inputs to the flip-flops. So here's T1 and T0, so here's flip-flop inputs. Alright, so what is T1? It's an AND gate. It's Q0 bar ANDed with X0. So T1 will be 1 when Q0 equals 0 and X0 equals 1. So Q0, X0 has to be 0, 1. So 0 and 1, that'll give me an output of 1. So, you know, normally I would do this by making a column for Q0 bar, and then I would AND it with X0. But I'm kind of skipping some steps because I'm going to run out of space here. So Q0 bar and X0. So this is going to be a 1. This will be a 1. These will be zeros because Q0 is a 0. This will be a 1. This will be a 1, and these will be zeros. So fill that in the usual way using, you know, a more disciplined approach. All right, T0 is very straightforward. It's just equal to Q1. So T0 is just going to replicate this Q1 column. So these will be zeros on the top half, and then 1s on the bottom half. All right, so we analyzed our circuit, we wrote equations, we used those equations to fill in the outputs and the inputs to the flip-flops. And now we're done with our equations, and we have everything we need here to finish analyzing the machine. So the next thing to do is figure out what the next state is. And we do that by figuring out, hey, if this is the input for T1 and T0, when the clock ticks, what's the new value for Q1 and Q0? So I write this as a Q1 plus, Q0 plus, and I label it next state. All right, well, remember what a T flip-flop does. If T is 0, when the clock ticks, the output does not change. So the new value of Q will be the same as the old value of Q. If T is equal to 1, then when the clock ticks, the new value of Q will be the opposite of the old value of Q. So it'll change from a 0 to a 1, it'll change from a 1 to a 0. This is sometimes called the excitation table for a flip-flop. It shows you how the outputs change when the clock ticks. And yeah, this looks like an XOR gate. Don't worry about that yet. But it is, you know, basically like an XOR gate. All right. So keeping this in mind, maybe having it next to us while we're doing this kind of problem, or just having it in mind, we can fill in this value for Q1 plus. What's the new value of Q after the clock ticks? Well, if Q1 is 0 and T1 is 0, the new value for the flip-flop is going to be 0. If Q1 is 0 and T1 is 1, the output's going to flip, so this will become a 1. 0, 0 will be 0, 0, 1 will become a 1. If our T input is 0, the flip-flop does not change state, so the new value of Q is going to be the same as the old value. So all 4 of these I can fill in a 0. And in fact, anywhere that I have a 0, I can just copy the current value of Q1. That'll be a 1, that'll be a 1. And since these are zeros, these will all be 1s. And when T1 is a 1, the current value of Q will get toggled, so this will become a 0 and a 0. All right, this is probably the trickiest part of the whole process, because if you just kind of go back and look at this table and don't understand where it came from, right? Why does this match this, and why is this the opposite of this, and why is this completely different from that, and this is the same, right? It's based on how the flip-flop works. What this flip-flop does is it says, hey, you know, if T is a 1, we're going to toggle the current value of the flip-flop so that 0 changes to a 1. If T is a 0, the current value of the flip-flop persists, and the 0 stays a 0. Alright, so now we can go ahead and we can do Q0, looking at T0. Well, T0 is 0 up here, and so these first 8 rows, Q0 is not going to change, so it's just going to be 0, 0, and 1. And these bottom 8 rows, T0 is a 1, so the Q0 value will toggle. So these will become 1s, and these will become 0s. And so now we're basically done. Now I did not explicitly go in and say this is state S00, this is S01, this is S10, this is S11, and so on, right? But since I'm using these names, I can do that mapping pretty painlessly in my head. I can look at this and I can say, okay, this is going to be S00, this will be S00, and so on. So we're good now to go ahead and draw the state transition diagram. And so these can take a few tries sometimes. But, you know, I'm just going to kind of start off naively and say, let's do S00, S01, S10, S11. And I'm going to make my key over here so I know what my picture means. And I'm going to list the state inside, and in the state bubble I'm going to list any more outputs. So now I go back to the original analysis and say Z1 is a more output. It depends only on the state. So I'm going to list Z1 in here. and then my transition arrow, I'm going to list my inputs, so I'll list x1, x0, and then I'll put a slash and I'll list any of the mealy outputs. In this case, there's only one, which is z0. So this is how I'm going to code my information. Each state, I'm going to list the name of the state, I'm going to list the value of z1, and on the transition arrows, I'll list the value of z0. Alright, well S00, the output is a 1, so this is a 1 down here. S01, the output is also a 1. S10, the output is a 0. And S11, the output is also a 0. And we can confirm that these outputs really are a more output because, you know, all of the conditions where this is the current state, this output has the same value. When we're in this state 0, 0, the output's always a 1. When we're in this state 1, 0, the output's always a 0. Well, that kind of confirms that this is a more output. Depends only on the state. But look at Z0. We're in state 0, 0, but half the time this output is 0, half the time it's a 1. That right there tells you this is not a more output. This has got to be a mealy output. It's got to be dependent on more than just the state. Because state 0, 0, well, the output could be a 0 or it could be a 1. So that's why we're listing Z0 on these arrows. Alright, well, we're going to have 4 arrows from each of these, so this is going to become a mess pretty quickly. But let's at least start this. So if your input is 0, 0, you're going to stay in state 0, 0. So I'll draw an arrow like this. And if you're in state 0, 0, your output is a 0. Your output Z0. If you're in 0, 0 and your input is 0, 1, you should go to state 1, 0. So if your input is 0, 1, you go to state 1, 0. And in that case, your output Z0 is a 0. If you're in 0, 0 and your input is 1, 0, you stay in state 0. So for input 1, 0, and in that case your output Z0 is a 1. And if you're in 0, 0 and your inputs are both 1s, you're going to go to state 2 and your output Z0 will be a 1. So we'll have another arrow here which says if your input is 1, 1, then your output's a 1 and you go to state 2. And so you would do this for all remaining 12 rows and you'll end up with a diagram. And, you know, this is a random circuit I just made up, so I don't think it's going to do anything particularly interesting. But that's the procedure for making the diagram. Alright, we're not going to have time to do a JK case. There's some examples in the book, but if our original circuit had had JK flip-flops instead of T flip-flops, what changes? Well, we'd have a J0, K0. If we had 2 flip-flops, we'd have a J1, K1, and so on. And so in this table, we would need to list flip-flop inputs like J1, K1, and J0, K0. So you'd have more inputs like that. We'd have more equations. We'd say J0 equals something, K0 equals something, and so on. And so we would have more columns that we would fill in for the flip-flop inputs. And then when we want to know what the new state is, we would use the flip-flop excitation table for a JK, which looks like this. If you have a J and a K and a current value of Q, what's the new value? Well, if J and K are 0, the output does not change. If j is 0 and k is 1, the output always changes to a 0. If j is 1 and k is 0, the output always changes to a 1. And if j and k are both 1, the output toggles. So your 0 becomes a 1 and your 1 becomes a 0. So that's the excitation table for a JK flip-flop. So when you fill out this state table, if you see, your current value is a 0, and j is a 0, and k is a 1, well, if j is 0, k is 1, current value is 0, the new value of the flip-flop is a 0. And so it's the exact same process, but these tables get wider.
What would be the key input? Is that
Sorry, say again?
what would be the K input? Like it could be anything like random?
Yeah, I mean, if we drew a circuit with JKs, then you'd have something going in here, and you'd have something going in here. And there'd be something in the circuit driving that.
I have a question about the diagram where you just do the circle.
Yeah.
The key where you drew the
Mm-hmm.
V1. You mentioned more newly. Which one goes where?
So the more output goes in the state, and the melee outputs go on the arrows. And that's because the melees depend on the state and the input, and these arrows tell you not only what state you're in, but what the inputs are. The Morse outputs only depend on the state, so we can just list them inside the state bubble itself.
Gotcha. Okay,
Alright, cool.
I had a question about the state transition table.
Yeah.
So I kind of you were going a bit quick. I couldn't follow along. So on your first row, you have your present state as being 0, 0, right?
Mm-hmm.
0, 0. Your Z input is 1, and then so what I'm confused about is you have two next states. You have Q1 plus and you have Q0 plus. So which one did you use?
Both.
To
Because your state is a combination of, what's the value of Q1 and what's the value of Q0. You have 4 possible states. So 0, 0 is a different state from 1, 0, is a different state from 0, 1, is a different state from 1, 1. So we're going to have 4 bubbles here, and we only drew, a start of it. But each of these represents a different combination of Q0 and Q1. Okay, cool. All right, so we did not get to talking about timing for state machines. We'll talk about that next class. But for now, you can skip that question on the homework. So I think the last question in the homework, question 5, I believe, shows a state machine and asks what the maximum clock frequency is. Skip over that. We'll talk about that on Monday. And it's a pretty simple analysis, but I don't want to rush through it because it's sort of one of the punchlines of this whole subject. So just do those first 4 questions on the homework, and we'll go over timing next time. All right, we are out of time, so have a good afternoon. If you want to go over any of this, you can come by lab hours tonight, and or office hours Thursday or Friday morning. And if I don't see you in one of those, I'll see you next week. Have a great weekend. Take care, everybody.
Awesome. Thank you so much. Bye.
Bye.
have a great weekend.
Thanks, you too.